Okay, so now let's see what else there is. Well, there's various special cases. One is, and maybe this is one of the things you're interested in, is the probability of, this is sort of alternative events. So probably the union of A and B is going to equal, well, let's see what it equals. It equals the number of elements in the union over the size of the sample space. And this then equals, well, we have a formula for the number in the union. That's the number in A plus the number in B minus the number in the intersection, right? Over the sample space size. Well, so this is just for general sets. Now, so if there's an intersection, then that decreases. But what happens if the two sets, if this equals 0? Well, and this is the case, the two events are said to be mutually exclusive. Okay, and then in this case, the probability of the union of A and B, well, since this is 0, is just going to equal the number of outcomes in A divided by S plus the number of outcomes in B divided by S, which is just going to, let me just write that out, which equals the probability of A plus the probability of B. Well, if you remember that when we did counting, it's sort of like if two events are mutually exclusive, the number of ways of making those choices was the sum. So we have this sum rule that for mutually exclusive events, the probability that either occurs is just the sum of the two probabilities. So that's like alternative events, one or the other. And so it depends on this probability here, but if that's 0, then you have a simple sum rule. And this is the mutually exclusive case here, in which you have a sum rule that if the events are mutually exclusive, then you just add them. And then we have the case of complements, that if the same way with, these are set identities that occur, that sort of, and we use this principle of the complement when we did the birthday problem. Now, here's something else. If events are not mutually exclusive, they can both occur, and we can ask what probability is that they occur. This is just the probability of the intersection. Now, this is where we bring back so this is the case in which we're looking at, it's not equal to the null set. Well, we can say the probability of A given B, by definition, is the probability of the intersection of the two divided by the probability of B, but the probability of B given A is equal to the probability of the intersection divided by the probability of A. Well, if you look at these two, see, the intersection is the same as both. So let's multiply the top equation by the probability of B to get the probability of B times the probability of A given B equals the probability of the intersection. And let's multiply the second equation by the probability of A, because the probability of B on the first equation cleared the denominator here in the same way here. So these are just the same thing. So we can, if the right-hand sides are the same, we can equate these two, and we can write the left-hand side here's the probability of A given B times the probability of B. I reverse the order, and the probability equals the probability of B given A times the probability of A. Well, that's a weird result, right? just an interesting connection between conditional probabilities. And I think this goes back to that first question of the connections, what this, because what happens if the probability of, well, let's look and see what happens if the probability of A and B are independent. If A and B are independent, then the probability of A given B equals the probability of A. Well, on this first first equation, that's going to be the probability of B, substituting the probability of A for that times the probability of A equals the probability of the intersection. And it works both ways, that if because of this equation here, like if I use this formula in this equation here, right? If they're independent, then the left-hand side is the probability of A times the probability of B equals the probability of B, A, probability of A. Well, this side cancels left and right, which means if one of these is true, if this is true here, this formula star, right? What it means is that the other one has to be true too. That the probability of B, A, has to equal BA. So that can, what we saw above, if one of these is true, if one of these indicates it's independent, it's necessarily true that the other one does too. And we can see from this result here that the probability of the intersection of A and B equals the probability of A times the probability of B. So we have these two interesting formulas. Now this is for independent events. Now, independent events can only occur when this is not equal to zero. Because if this was equal to zero, if the intersection was equal to zero, then both of these probabilities would have to be zero, and that's not the case. So for independent events, means that they have to intersect. And then the probability for the intersection is going to be this product of probabilities. And then we saw the probability of the union for mutually exclusive events was equal to PA plus PB. And this is sort of like, if we remember back when we did counting, we had these two principles, a multiplication principle and addition principle. And the addition principle occurred when we had mutually exclusive events, and the product rule for counting applied when we had independent events. And so anyway, this is just an interesting sort of like reflection of those ideas, and that there's something going on. This simultaneous events is a name for, if you have an experiment and outcome occurs, and the intersection is both A and B occur, the probability, if events A and B are independent, is the product of the probabilities. So this is again looking at and there's an example here where you have we're looking at connections between events. And then there's one last topic here, which is where there's a case of maximal dependence. That's when the opposite of independence, it's when one set is a subset of the other. Because if you have the probability of B given A, if B is a subset of A, it's going to be this ratio of probabilities. And the second expression is if one knows that A has occurred, then the second expression follows because the problem. Okay, well, let me go and do this more slowly. Let's look at the case when you want to look at the probability of, no, that I know what I just said wasn't clear. So let's start again. Probability of B given A when B is a subset of A should be the probability of the intersection of A and B over the probability of A. Well, if since B is a subset of A, this intersection is just going to equal B because B is inside A. So because if B occurs, then A occurs. So that's the, okay. And I think that's what this result here. And the second expression occurs because this. Then okay, so you can see that unless the probability of A, okay, so the probability that B occurs, if A occurs, equals, if there's a if B is a subset of A. Well, this is a case when you were interested with this was, if this was independent, P of A would have to be equal to 1 for in this case to occur. And that's not quite what's going on here. Okay, let's look at the other one for this situation. The probability that A occurs given that B occurs, but still with this constraint here. This is the probability of the intersection of A and B over the probability of B. Okay, well, this intersection here is still the probability of B which equals 1. So that in this case, B guarantees that A occurs. So in some sense, this is the case of sort of maximal, this is what I call the case of maximal dependence, in which you have this sort of situation here occurring. And then if you look at the other way around, if you have a case of maximal dependence, you can also look at the flip side here. Okay, so there's been a bunch of formulas here and results, and here's the definitions. There's a page here where we review all these formulas. Events A and B are mutually exclusive if their intersection is 0. Here's the definition of conditional probability, and in terms of that definition, A and B are independent if the probability of A given B is equal to the probability of A. And then here's just all those formulas that we went through, so you can look at these if you need to refer to them.